Hi everyone, welcome to this C++ feature. My goal is to help you write efficient C++ programs. In this video, I'll discuss one of the confusing features in modern C++, which is constexpr. What is it and how to use it in the situation that we should use it will be discussed in this video. So let's go to it. To understand the constexpr keyword in C++, we need to understand two things, compile time and runtime. If you haven't heard this word, you can go and check the video I will provide you in this channel. So to summarize, during the compile time, the compiler will check for syntax and semantic errors, and also fixing errors is possible because the compiler will output the error and we can follow and fix. And during the runtime, what has happened in the execution is the computation. For example, arithmetic computation, for example, the memory allocation, the runtime errors like logical errors and memory leak will occur in this state. Also, programmer can handle with these error by using the exception handling, which is happen in runtime. So if you understand these keyword compile time and runtime, what is next? So let's come to our next questions. Context feature, what is it? Context features blur the line between compile time and runtime. What it means that when you write a program, the execution mostly occur in runtime, like initialization of the variable, like the control flows, like calculation, which almost basically happen in runtime, right? But in the compile time, we use the results uh, just for syntax error and also semantic error checking, and also the code binding, something else. But what if we want to do the calculation in compile time? Why we do that? Because if we do shift the task from runtime to compile time, that means our runtime execution will be much faster or will be benefit a lot from compile time execution. Let's see how to use constexpr with an object. Assuming that we have a variable named array size, which is declare constexpr and is initialized to 1000. So this means that this object is known, the value is known at compile time and also it's constant, right? It's not so interesting. The interesting part is that when we can use the object as integral type. So let's see what I mean by that. So we have a variable type array of int and also the size is 1000. This is very simple, right? And 1000 is a constant and it's a cipher array defined at compile time. What if we want to replace 1000 with variable? The variable name size of type integer and is initialized to 1000 is replaced with 1000. So yeah, it's right like this. Compare to if we replace 1000 with array size. What do you think which one is correct or incorrect? Yes, the correct one is the right size because the value of array size is known at compile time. And the array is the constant, container, which is defined at compile time. So we need to use the variable that has the value known at compile time, right? This is so important. It is a fundamental concept of constexpr. And let's see another case. Let's say we declare constexpr with the variable type vector and string. The vector can be allocated dynamically at runtime, also the string as well. So with this type cannot be used at the compile time. The type that can be used as compile time is the literal type. So the literal type means that the type that is value is constant and known at compile time. For example, the fundamental type like integer, double, char, bool, and etc. Um, the array of literal type, the reference of literal type, pointer of literal type, and finally the user-defined class that is data member um, is the literal type. Also, they have at least one constructor that is defined constexpr. Another use case of constexpr is with the function. This has the interesting meaning. If we define the function with constexpr, like this example, we have the function multiple, which return integer and is defined constexpr. The meaning is interesting because if the input parameter, like in this case, we have x and y, if they are constexpr, they are like in the previous slide, we have the object which is constexpr. If both x and y are constexpr, this function will return the constexpr. You see, this calculation multiple is a multiplication of x and y. The calculation will return the value which is known at compile time. Let's move to the next one. If we declare constexpr to the variable x initialized to 1, this similar example, and also we also use the array of type double, and instead of just a fundamental object or the constant, we can replace those with the constexpr function here. Why? Because we have the variable x, which is constexpr, and also 2 is constexpr, known at compile time. So it's so interesting as you can like calculate things in form of function which has the value known at compile time. Not only that the value can be known at compile time, what if we can use the multiple function with as the normal function? We can do like that. If not both x and y are constexpr, like they are just typical integer, this function multiple can be used as runtime as well, like a normal function. If we, return the multiple of 2 and 3 to the variable products, you can do as well. And this calculation is done at the runtime. That means we should declare constexpr, whenever possible, because we can do at runtime and compile time as well. If I define the user define struct or class, like in this example, the point struct, we can do as well with the constexpr declaration. And why do that? I do this because from the previous slide, we can use the constexpr with a literal type. This struct point is the literal type, because it meets the requirement. It has the data member like double, which is the literal type. It has at least one constexpr constructor like this, and also its member function can be declared constexpr as well. So we already know how to use constexpr keyword with function and object. So here is how they can be interact. On the left is like the constexpr, struct that is the same as the previous slide. And on the right side, if we We can use the struct point with the function that we define as constexpr. Like in this case, we have the function midpoint, which take into account the P1, which is a struct point, and the P2, which is a struct point as well. So these, two objects can be interacted, and with this function, this can return type point with constexpr. And if we declare the P1 with the constexpr and also P2 with the constexpr, and also we can create the object myth, which is constexpr as well because P1 and P2 they are constexpr. In standard library or SCL, many functions support constexpr, and this keeps growing. For example, in C++14, constexpr support for loop and while return type. In C++20, constexpr support many functions like accumulate, transform, and etc. So my suggestion is that always check for which functions support the constexpr in documentation like in C++ reference. We have discussed several points so far in the slide. So here is the code implementation that use the constexpr and illustrate and different cases. Let's start with the first one. We have the integer type in array, and you can see that we have error here, like the rate underlined. So this can be interpreted as, the value is not known at compile time. If I run this source code in C++, I will move to C++20 because it's open to more context. So you can see that in errors of JS, I'm sorry, another report that size is not a constraint expressions. Yeah, so we can use this one. For the next case, this is what is wrong with this. Let's analyze. So we have the size variable and we declare another one as array size. This is naive and trivial. So array size is initialized as size. This is wrong because although we have the cons here, this is not cons expression and cannot be used in array. If I compile it, so the same errors appear. It's not a constant expression. Let's move to another one. If we have the array size as constexpr, yeah, it's exactly the same in the slide, and it is valid. It's legal. Let's move to another one. This is interesting part. We declare constexpr with vector and string, but there's no error shown here. If I compare here with the C++20, it works. No error. But in the slide, I told you that constexpr cannot use with non-literal type. But why is it work with this? Let's go back to the previous version. If we compile with C++14, we got error. And the error is non-literal type used with constexpr. So here's the thing. In modern C++, since C++20, constexpr expand the capability to use with many functions and also the literal type like this. That means we can allocate and deallocate memory during the compile time. This is so useful and optimize our code. This is a fact that constexpr should be used whenever possible in C++ like 20 or more, because the goal in C++20 is to enable more compile time programming. Let's go to the next part. If I have this, the user-defined type point, as a constexpr, and also the member function of the point that I have. It can also be constexpr, and the definition of the point is defined here. So it is a struct that has a at least one constructor as a constexpr, is one, and the member function can return a constexpr, and this one is allowed because the literal type in data member. So let's move on. Um, let's move on to the next one. So here, hmm, this is exactly in the slide where we can use the function to return the constexpr and can be integrated in the, like lit in the integral type, like in array. Let's move to the next one. If I have, this is the user-defined type as well. This is the interaction of the function object with the constexpr. This is the, I declare P1 and P2 with constexpr, and then use P1 and P2 point in the midpoint function to calculate the midpoint between the point 1 and point 2. This one can also return the constexpr as the definition of the function defined here. So it takes the user-defined type in and also return as the point with the constexpr. It's so useful as this is not a member function and can use for object interaction. So yeah, and that's all for the rest is my experiment on how to use a constexpr. So that's all the point I have here. And lastly, here's a use case of the constexpr in real-world application of the particle filter in the subject of robotics. Here I have the library from Ecumen. Um, so here is showing that this is in C++20. So you can see from the README page that it is used in in C++17 and maybe update to C++20 or more. So here in the code you can see the template programming where they use a lot of constexpr. Here you can see this is the struct object definition. They use constexpr to enable the complex compile time programming, so you can explore and check whether you can understand. If you don't understand, you can like look on the documentation and they will explain about how to use a constexpr. And also, I have covered all the points of use constexpr so far. So yeah, thank you for watching and hope you explore more and use apply to your application. Thank you.